Hello everyone! In this video we will continue to examine topic 1.2, uncertainties and errors, and in particular we will begin to discuss propagation of uncertainties. Alright, so this is the kind of video you're going to want to watch and you're going to want to bookmark for the first time you need to do a lab. Propagation of uncertainties is one of the trickier things to do in sort of laboratory analysis once we're done actually taking data. And here's the general idea. Often we will measure different quantities. So we'll measure heights or distances, we will measure times, we will measure currents, for example, and then we will do something with them. We will make a calculation and we will find a different value, okay? When we find that different value, it's very, very important that in calculating that value, we also have a way of understanding what our uncertainty is on that value, given the uncertainties on the original measurements. So if we are doing something mathematically with our data, processing it, we need to do what is called propagating the uncertainty through that calculation, figuring out what the uncertainty is on our calculated value, given the uncertainties on our actual values. So, as a simple example, let's consider addition and subtraction as operations first. Imagine that you're going to measure the height of one person, a small person, standing on top of the head of another person. Okay, so imagine you're measuring the height of sort of this two-person thing. You want to calculate that height. And actually, what you are directly going to measure, though, is the height of the first person and the height of the second. And then you're going to add them together. So this is an example where you're going to propagate your uncertainties through the addition. You have an uncertainty on that first height and an uncertainty on that second height. Okay, what is the uncertainty on those two heights added together? Well, for adding, here's how it works. If your height 1 measurement is 1.4 plus or minus 0.2 meters, and your height 2 measurement is 1.8 plus or minus 0.1 meters, then your final height will be measured as h1 plus h2, 3.2, plus or minus the absolute uncertainty of the first measurement, plus the absolute uncertainty on the second measurement, plus or minus 0.3 meters. In other words, h1 could have been off by that first amount, h2 could have been off, so h1 could have been off by 0.2 meters, like so. H2 could have been off by 0.1 meters, like so. And so your final measurement will need to include the uncertainties on both sort of those input measurements. And the way you figure out what that uncertainty should be is you simply add the absolute uncertainties. 0.2 plus or minus 0.1 equals 0.3 meters. Notice the way I'm describing this. You are adding the uncertainties here, but it is not because you are undergoing addition. It's because that represents the total amount of uncertainty on the final value. No one messes addition up in that particular way, but they do sort of mess up subtraction. So consider the following situation, right? Again, pretty silly. What you're going to do is measure the difference between the height of person 1 and the height of person 2. You're interested in, for example, how high off the ground person 1 would be if person 2 grabbed them by their ankles and held them up. Okay, so you're interested in sort of that difference in the height as shown in this picture.
Sorry, I couldn't quite hear you.
I'm sorry, Siri just turned on. But what you're going to do is subtract h2 minus h1 to get that value. And you'll go ahead and do that. That's 1.8 minus 1.4 meters is 0.4 meters. But then the uncertainty on that value also gets added. Okay, so the uncertainty on h1 is plus or minus 0.2 meters, and the uncertainty on h2 is 0.1 meters. Those uncertainties still add up. Because imagine h2 is off in the positive direction, and h1 is off in the negative direction. Right? you've still got sort of a gap of 0.3 meters on either side. Same for H2. What if H2 were smaller than we thought it was by 0.1 meters, and H1 was larger than we thought it was by 0.2 meters? So in order to get the estimated uncertainty on the subtracted value, you also add the absolute uncertainties on H1 and H2, giving you a final measurement for the difference between their heights of 0.4 meters plus or minus 0.3 meters. Notice this is a much, much larger relative uncertainty for the subtracted case than it is for the added case. And that simply reflects the way that the uncertainties work. The final value on the added case is probably around 3.2. But the final value on the subtracted case has a sort of huge range that it could be because of the uncertainties on both of these measurements. And so the relative uncertainty, even though the absolute uncertainty is the same, the relative uncertainty is much, much larger on the subtracted case. Now this is shown in your data booklet with the following general formula. So you don't have to memorize this, but you do have to sort of identify the equation. In your data booklet, it will say that for any quantity y equal to a plus or minus b, then the uncertainty on y is equal to the uncertainty on a plus the uncertainty on b. Notice there's no minus in there. So I'm going to say that again. If any quantity y is equal to a plus or minus b, then the uncertainty on y is equal to the uncertainty on a plus the uncertainty on b. That is an example of propagating uncertainty through addition or subtraction. In both cases, you add the absolute uncertainties.